There is grandeur in this view of life.
Welcome to Evolution Talk with Rick Coast, an introduction to the oldest story ever told.
It's extremely difficult to predict what will happen in human evolution. If we send out colonists to colonize space stations or other planets, as some people in a science fiction sort of way speculate, then that will be rather like a sort of celestial Galapagos, where there's rather little gene flow between islands of colonization. And there might well be the opportunity for divergent evolution. And if we colonize a planet with, say, a weaker gravitational field than we have here, or a stronger gravitational field than we have here, then you could actually predict certain changes in the skeleton, where if a planet with a strong gravitational field, we would have great stumpy rhinoceros-like legs to support our increased weight, whereas on a planet with a weak, if we could set up a colony on the moon, then we'd probably evolve towards being like little spidery things skittering around on long spindly legs, provided that survival was non-random, provided it was possible to die before you reach reproductive age, which in our civilization is quite difficult to do. So there are all sorts of unknowns, all sorts of strangenesses which have been brought about by the uniqueness of humans.
And that was Professor Richard Dawkins, taken from a lecture that he gave at the Cullum Science Center in 2012. And what I want to focus on isn't the actual words being said, but the implication behind them. What Professor Dawkins is implying is that, given a set of variables, we can speculate on how something might evolve. But that's all we can do, is speculate. We can make broad predictive strokes when it comes to how an organism will evolve. And that's it. What those changes will look like, if they happen at all, is beyond our power to know. We have more luck predicting when the next snowstorm will hit my little town in New Hampshire, which is no luck at all. Now, does this mean that theories about evolution are outside of the realm of true science? A strong theory is testable. After analyzing a set of results, you can make predictions. When I mix yellow liquid with blue liquid, I'll have a green liquid. I can vary the shade of blue by varying the mixture. I can add red and the color will be different. I can then say that whenever I add blue and yellow together, I will get green. Blue and yellow being my primary colors and green being a secondary color. I can tell you about this and even how to test it. And knowing all of this, you can be pretty sure that when you mix the two together, the blue and the yellow, precisely following my very complicated instructions, you will get green. It's testable and predictive. I predict green, test it, and the result is green. We can try to tweak it or falsify it. It's scientific gold. But what about evolution by natural selection? It's a scientific theory. But can I test it or make a prediction? I suppose I can try, but what sort of prediction would I make? What factors can I tweak? Can I say that when I add a gene from this animal to that animal, that something in particular will happen? Well, actually, I can. But that's for another episode. But the point is, we can't predict what will happen to an organism by tweaking environmental variables. We can't predict how it will evolve. Even if we were to do so and are able to observe an evolutionary path, it's highly unlikely that we can replicate that test. And this has been one of the criticisms that evolution research has faced. Philosopher Karl Popper is famous for saying that evolutionary biology lacked any predictive power and was therefore untestable. He recanted this later on, but in his statement, there is a bit of truth. Or is there? Is it possible to raise ideas and theories about evolution above being simply matters of conjecture? The answer, of course, is yes. And to better understand the predictive power of evolution, we must first chew on what it means to formulate a theory of prediction. We can then get to the real meat of the matter. But let's first take physics. Physics has always fascinated me. We know so much about the world on a macro level that we can predict with confidence what will happen given a set of initial conditions and variables. It's how we are able to send ships to the moon or triangulate your coordinates so that you can navigate from here to New York with the GPS app on your phone. Without the predictive power of science and repeatable tests, we would be able to do none of these things. We can bang flint stones together just right and get fire. If we sometimes got snowflakes instead of fire for no apparent reason at all, we wouldn't have made it very far as a species. We might still be hiding in caves and waiting for the sun to rise in order to hunt for raw food. But we depend on the world around us to follow certain rules just as much as we seek to understand those rules. Prediction is power. Now that's on the macro level. We can even perform tests and make predictions on the microscopic level, but push past that into the realm of the quantum level, and our predictive powers begin to fall apart. In fact, we see many strange things that are unexplainable, for now at least. Theoretical physicist Richard Feynman is credited with saying that if you think that you understand quantum mechanics, you don't. Quantum physics is too strange. Particles appear to pop in and out of existence or become entangled so that one particle appears to be tied to another particle, no matter how far apart they are separated. Particles behave like waves and waves like particles. At the quantum level, determinism appears to be false. Prediction flies out the window. But that doesn't stop science from studying it and attempting to test it. We can also make predictions about what might happen under certain situations or certain conditions. That's because we can observe what has happened. Let's look at this another way. I mentioned the weather and snowstorms. If you live in New England, you know how unpredictable the weather is during the winter months. It's almost ridiculous to even try. This past winter, there were massive snowstorms predicted that never appeared, even when those predictions were for the very next day. There's one in particular that was practically promised to hit, so we prepared for it. I had the generator gassed up and it was ready to go, and we expected school to be canceled, and I planned to work from home that day. We went to bed expecting the worst, and we woke up the next morning to blue skies. The storm, overnight, had veered north of us. Maine was slammed while we went on with our normal daily lives. Sorry, Maine. My in-laws live there, and they were hit by the storm that was supposed to hit us. We can't predict what atmospheric conditions will be like with any level of certainty, especially the further out that we try to predict. There's simply too many variables. There are too many things that will affect the outcome. But that morning when I woke up to blue skies and turned on the news, I could watch the weather videos, listen to the meteorologists interpret the data, and understand what happened and why it happened. You can see it all laid out and it makes perfect scientific sense. The meteorologists can explain it because they've seen it before and they understand it. After many years of observation and data collecting, they understand why the storm missed us. I might not, and that's why I turned to them. Now, does that make the science studied by meteorologists less powerful because it can predict weather patterns with 100% certainty? Of course it doesn't. They study what has happened and apply that understanding to what is happening. After the fact, they use the knowledge gained to better their understanding. And how about another example? What about forensics? We can't predict when a crime will happen. That's saved for science fiction. But once it has happened and the culprit has left the scene, it's time for forensics to step in and piece together what happened or what occurred. Using science, they can tell you where someone was standing when a fatal shot was fired, how they entered the room, and how tall they might have been. And if they left any fibers behind, they can even tell you what they were possibly wearing. Like with meteorology, a forensic scientist pieces together the past. So what's the weather going to be like a week from today? Nobody knows. Even the world's most powerful computer can't tell you. We can't feed all of the variables into it that it would need to calculate such a thing. But given enough data from the past, it can begin to decipher patterns or recognize patterns that occurred in the past. And using these patterns, meteorologists can make retrodictions. A retrodiction is simply a prediction set in the past. Let's step back into the world of evolutionary science. Retrodictions rule when it comes to understanding how organisms have evolved. Let's look at dolphins. We can plot 3 points in time. We'll call these 3 points A, B, and C. A is located in the distant past, B is the more recent past, and C is 10,000 years from now. Using the fossil record and genetics, we can begin to see how it is that dolphins evolved from point A to point B. We can make retrodictions as to the evolutionary path their ancestors walked to develop from point A to point B. But C, where they will travel and what changes they will have undergone 10,000 years from now, that we can't do.
But you know the starting conditions and you know the drivers, and so you can actually calculate what you'd expect the outcome to be. I think it's just too complicated for that.
But knowing where an organism started out on the tree of life and knowing where it is now, well, that allows us to uncover branches we didn't even know existed. Having the right information makes retrodictions possible.
Ideally, it'd be nice to do experiments as well, by the way. And the problem there, of course, is that it all takes rather longer than a human lifetime to do.
The problem is, evolution moves slowly. And by the way, I didn't make the word retrodiction up to prove my point. A quick search using Google's Ngram viewer shows the term being used in 1877. The first appearance I could find was in a book published by the New York Academy of Sciences. Charles Darwin knew the power of retrodiction, even if he didn't have a word for it. He predicted, while studying the possible development of humans, that our ancient ancestors most likely walked out of Africa. We now know this to be true. Both fossils and genetic evidence supports that theory. And then there are the Neanderthals, a favorite subject and mystery of mine. Now, what happened to them? I've already dedicated 2 episodes to Neanderthals, and in them I covered the proposed theory that we gradually assimilated them. Again, genetic evidence is in support of that theory. DNA studies show that some of us, depending on our lineage, have very small genetic traces of Neanderthal DNA present within us. But the best example of the predictive or retrodictive power of evolution comes with the example of the discovery of Tiktaalik. To me, this one is the granddaddy of all examples. And if you're not familiar with it, Tiktaalik is the fossilized remains of a creature that lived 375 million years ago. It was discovered in 2004 by a team led by Professor Neil Shubin.
Since I was a graduate student, I was interested in one of the great evolutionary events in Earth history, which is the transition from life in water to life on land. And you think about that, and it's a remarkable transition because so much in the animals have to change.
And that's Professor Shubin. And that's what Tiktaalik represents, the transition of fish with gills and fins to land-dwelling tetrapods with lungs and legs. Sometime between 380 to 365 million years ago, this transition happened. Tiktaalik represents that transition. Professor Shubin calls Tiktaalik a fishapod. And here's what makes Professor Shubin's discovery so amazing and the perfect example of the predictive power of evolution. He didn't find the fossil out of sheer blind luck as so many people sometimes do. What he did was this. He knew about the fossils of fish from point A, that being 380 million years ago, and he also knew about the fossils of land-dwelling tetrapods found at point C, 365 million years ago. So somewhere, at point B, there existed a creature in between the two. If the fish-like animals at point A evolved to become the tetrapods at point C, using the theory of evolution by natural selection as a tool, he then knew what those organisms at point B might look like. Now, he didn't pick a random spot and start to dig for it. Instead, he figured out where he could find a fossil of what he was looking for, walk up to it, and dig it out of the ground.
One of the best places and most unexplored places to look for such a fossil was in the Canadian Arctic. We discovered it from a geological textbook, not the scientific literature. It was completely accidental. But it turns out these were the perfect rocks of the right age and exposed at the surface to produce such an intermediate.
Now that's science at its best. He could have dug anywhere, but using his knowledge of geology and the way species have evolved, he was able to find exactly what he was looking for in the exact spot he expected to find it.
So a real remarkable transitional creature. It had both lungs and gills. And what's exceptional about this is just how ordinary it is, in the sense that it's exactly the intermediate that you would likely predict. So what this does is it tells us a lot about the shift from water to land, along with the other creatures. So there are hundreds of other fossils that colleagues around the world have found. It tells us a lot about how this great transition happened.
I'll give you one more quick example. This one, at least the prediction itself, predates Professor Schubin's discovery by about 150 years. It was made by Charles Darwin while he was studying plants in 1862. There wasn't much that Darwin didn't study. From barnacles to chimpanzees, Darwin was fascinated by the tree of life. One of the things that captivated him was the way flowering plants reproduced using pollen. There are quite a few methods of getting the pollen from one plant to another. In some cases, the wind is involved. In others, the plants have evolved flowers to attract insects. A classic example of this are bees. Bees will land on a flower looking for nectar, inadvertently cover themselves with pollen, and travel to the next flower, spreading the pollen. The plants use bees to pollinate. The bees benefit from the flower, and the flower benefits from the bees. It's a match made in heaven. The flowers evolved to use bees in the pollen delivery process, and bees evolved to use nectar. What fascinated Darwin was a species of orchid from Madagascar that had an extremely long nectary. This is the part of the flower that produces nectar, the sugary liquid that some insects love. The orchid Darwin was looking at had a nectary about a foot long. Now, this puzzled him at first. The nectar collected at the bottom of this extremely long nectary. He realized that the flower must have evolved this way to protect its nectar from being collected by an animal that couldn't help it. But what insect could ever reach it? In Darwin's words, and this is a quote, "What insect can suck it?" He predicted it had to be a moth with an extremely long proboscis. The problem was, no known moth had a tongue that long. 20 years after Darwin died, the moth he predicted was found. A large moth with a tongue a foot long. But did this moth actually use this tongue to get the nectar from Darwin's orchid? That question remained unanswered for almost a century. If you go to evolutiontalk.com/orchid, it will bring you to the page for this episode. You will also see an incredible little video of this very moth, its long tongue, and Darwin's orchid, filmed by Professor Philip DeVries from the University of New Orleans. So what sort of creatures will this planet be populated with in, say, 50,000 years? No one can say. Just like we can't predict what the weather will be like or the state of technology. That, of course, if there is anyone left to enjoy that technology 50,000 years from now. If things go the way we think they will, based on the past, we can say that the planet will most likely still be here, and also that life on this planet will continue to evolve. Mankind will evolve as well. Whether we are looking out at the universe with two organic eyes or enhanced cybernetic eyes, the chances are that what we will see will be, in a word, beautiful. Evolution Talk is written and produced by myself, Rick Coast. The music on this episode was composed and performed by Poddington Bear. The support from Evolution Talk comes from you simply by listening. Your support is greatly appreciated. You can always reach me at the site's contact page or on Twitter, where you can find me at Rick Coast. And most of all, thank you for listening. And until next time, please take care of yourself. We can bang flints together, or flint stones together. Flintstones. Okay.
Evolution Talk is a Rick Coast production.